Okay, great. So let's continue our lecture. We are studying Turing decidability and Turing recognizability. Uh, First, I want to introduce some terminology. So, Turing recognizability is sometimes also called recursively enumerable. So, Turing recognizable languages. mm, Also known as recursively enumerable languages. Turing decidable languages are also known as recursive languages. This word enumerable has to do with the fact that elements of Turing recognizable languages can be enumerated by a Turing machine. We'll talk about that soon. But these words recursively enumerable and recursive, these are very common, almost as common as words as the phrases recognizable languages and decidable languages. So it's good to know both sets of terminology. Okay, uh, so let me draw a nice Venn diagram. This is all languages. It's huge. The set of all languages over a finite alphabet sigma is an uncountable set. Sitting inside this is, okay, so there's also regular languages. That's a really small corner. Regular. Then a bigger subset of that is decidable languages. An even bigger subset, well, possibly even bigger for all we know, an even bigger subset is Turing recognizable languages. All these three subsets, regular, Turing decidable, and Turing recognizable, are countable. So they are much, much smaller than this collection of all languages. So this picture is not to scale. Okay. Now there's an important notion closely related to Turing recognizable. It's called co-recognizable. So a language is co-recognizable if its complement is recognizable. What does that mean? So you have a language. It The strings that are in it right. So I'm just opening up the definition of what of recognizable in this. So so L is co-recognizable. Co-recognizable if uh, for X. So if there is a Turing machine M, there is a Turing machine M such that uh, one, if X is not in L, then M on input X halts and accepts. If X is in L, then either M on input X halts and accepts, halts and rejects. This is option 1. Or uh, loops forever. Every decidable language is also co-recognizable. Why? Well, the Turing machine that decides the language, for x's which are in the language, it halts and accepts. For x's which are not in the language, it halts and rejects. So you can take that Turing machine, and instead of accept, whenever it was about to accept, you reject, and whenever it was about to reject, you accept. So let me write that observation down. So we already know that decidable languages are recognizable. I was just saying that every decidable language is also co-recognizable. So if L is decidable, and this is, I guess, a fact which we're going to prove. So it's not a fact. Facts are things that I don't prove. Claim. If L is decidable, then L is co-recognizable. Well, you could prove it in two ways. One is you could say that if L is decidable, then the complement of L is recognizable. Oh, sorry, if L is decidable, then so is the complement of L. And since the complement of L is decidable, the complement of L is also recognizable, which is the same as L being co-recognizable. So, okay, let's say it that way. So, proof, if L is decidable, then the complement of L bar is also. And the sub proof of that is whichever Turing machine decides L, we can switch the accept and reject states. And that decides L complement. That decides L complement. You can't do the same thing, or at least it's not obvious whether you can do the same thing for recognizable languages. Is it true that if L is recognizable, then L is also co-recognizable, or equivalently, if L is recognizable, then L complement is recognizable? Well, we would like, what if you try to do the same thing? So whenever X is in the language, you know that this, so you have the Turing machine, so that whenever X is in the language, XX, the Turing machine halts and accepts. But in the other case, it either halts and rejects, or it goes into a loop. You can switch accept and reject, and that will, to some extent, it will do some of the job. But what about all the x's for which the Turing machine goes into an infinite loop? You can't say, oh, if the Turing machine goes into an infinite loop on X, then halt and accept. You can never know that the Turing machine has gone into an infinite loop on a given input X. Since you never can arrive at that conclusion, you can't decide to, okay, instead of going into this infinite loop, let me instead accept. That's what we would have liked to do. So the statement that if L is recognizable, then L complement is also recognizable, uh, does not have, that statement may not be true from what all we know so far. Good. So if L is decidable, then L bar is also it's also decidable. Since L bar is decidable, L bar is decidable, L bar is recognizable. And so L is co-recognizable. Okay, so up in our Venn diagram, we can add in an extra bubble, which looks like this. These are the co-recognizable languages. Turing co-recognizable. Good. What I'm now going to show is that this region, this is the languages that are both recognizable and co-recognizable, but not decidable. There's no such region. So this does not exist. That's what we're going to show. So let me show you. This is a very nice and basic theorem. L is decidable if and only if. So this is a theorem because it's important, and I'm proving it. It is decidable if and only if L is recognizable and L is co-recognizable. Okay. We already saw the one direction proof. We already saw the forward direction. If L is decidable, it's recognizable. If L is decidable, it's co-recognizable. In the other direction, now this is a really nice proof. What do we have? We know that L is recognizable. So we have access to it. So we know that there is a Turing machine which, given an input X, runs for some time, or possibly a lot of time, possibly forever. But if X was in the language, this will halt and accept. If X was not in the language, it may halt and reject, or it may go into an infinite loop. But it doesn't halt and accept. That's not okay. Similarly, since L is co-recognizable, we have a similar Turing machine, which, given an input X, if X was in the language, who knows, it may or may not halt. It may, it either, oh, sorry, not who knows. It may either halt and reject, or it may loop forever. And if X is not in language, then it definitely halts and accepts. So for this, assume L is recognizable and co-recognizable. So because it's recognizable, so we know there exists M1, a Turing machine M1, and also a Turing machine M2, such that one, if X is in the language, M1X halts and accepts, and M2 on this input either halts and rejects or loops, but I'm not writing that part. If X is not in the language, M2X halts and accepts. We want out of this to produce a single Turing machine that on every input halts and either accepts or rejects, depending on whether X is in the language or not. So good. How do we do this? What prevented us from showing that every recognizable language is decidable was that there was this possibility that the Turing machine goes into an infinite loop when X is not in the language. And if it goes into an infinite loop when X is not in the language, I mean, you don't have the ability to say, okay, now let's do something else, because going into an infinite loop, you never know that you're done. But now you have access to M2, which can spot the x's which are not in the language too. So M1 and M2 together help you decide the language. So here is the new machine. So the new machine M on input X does the following, where it's going to be a decider for the language L. The following. Okay, so any suggestions? What do we do if with M1 and M2? Ah, I hear a suggestion. Oh, you say we run M1 on X first, and if it accepts, halts and accepts, then good, we accept. And then if not, then we run M2. Okay, let's see what's wrong with that. Is that a good? So the suggestion is let's run M1 first. And if it halts and accepts, then you know X is in the language. And after that run M2. But this is a problem. The problem is, what's the problem? The problem is when you run M1 on X, it may never stop. So you won't even get a chance to run M2. If you don't even get a chance to run M2, even though M2 was about to halt on an input X which is not in the language, if M1 didn't end up halting, you don't even get a chance to run M2. You want to get a chance to run M2 too. You could try the other option. First run M2 and then run M1. But that also has a problem. The problem being that, well, M2 may not halt. If X happened to be in the language and you run M2 first, then M2 may not halt. Then, yeah, who knows what happens. So the idea is to run both at the same time. Okay, so the new machine M does the following. It runs M1 and M2 on input X. So I guess M1X and M2X simultaneously. What does that mean? In every time step, you do one step of M1 and one step of M2. How do you do that? Well, your Turing machine has to somehow do what both those Turing machines do. The different Turing machines may move their heads differently. It's not clear how you would do it. Yeah. So you have to figure out how to do it. So it is true that you can set up a Turing machine that can do one step of M1 and then a step of M2 and then a step of M1 and then a step of M2 and a step of M1 and a step of M2. This requires a little bit of care in how you do it, but you can do it. So run. So in a high level language, it's definitely clear that you can do this. Just but at the Turing machine level, it requires some care. So run M1 and M2 X simultaneously. Okay, so requires some care. See the textbook; it's written very well. So okay. See the textbook. It's when you saw how to run two DFAs on an input X at the same time. That does capture some of the idea, but there's more involved. It's more complicated because Turing machines can write on the tape and the state of the tape can evolve separately. So executing one step of M1 really takes many steps for M, and executing one step of M2 takes many steps for M2. So for M2 ToO. So this requires some care. See the textbook. It involves scanning the entire tape and updating the positions of the heads to maintain the state of M1 and M2, including the location of the heads and the contents of the tapes, and updating it one step at a time. Okay, so good. So you run M1 and M2X simultaneously. If any of them halts, if M1 halts, halts and accepts, then M accepts. If M2 halts and accepts, then M rejects. That's the new Turing machine. And what it does is, for every X, it's going to halt. And easy to see, for all X in L, or for all X in sigma star, sorry, for every single input, M of X halts. Because X is either in the language or not. If it is in the language, then you guarantee that M1 halts and accepts. If X it's not in the language, then we guarantee that M2 halts and accepts, and so M rejects. MX halts and outputs the correct accept or reject thing. Okay, so that's this basic theorem that a decidable language is both recognizable and co-recognizable, and a language that's both recognizable and co-recognizable is decidable. So in this Venn diagram, you do not have any region which is both recognizable, co-recognizable, and not decidable. The intersection of Turing recognizable and co-recognizable languages is this set of decidable languages. Okay. So the final thing that I want to talk about now is, okay, so let me also mention that it's a theorem, and it's a very important theorem, that there are languages that are decidable, that are recognizable but not decidable. So and there exist languages such that L is recognizable but not decidable. And by the theorem above, it automatically means that L is not co-recognizable, because if it was also co-recognizable, then it would end up being decidable. Okay, this is an extremely important theorem. This is Turing's theorem. And it's one of the cornerstones of computer science. There are so this is a language which, yeah, it's reasonably explicitly defined. That's the recognizable part, but it's not decidable. So there is no algorithm that always halts and tells you what the answer is. And I can tell you what that language is. The language itself is quite simple. The language is called ATM. Sometimes there's a closely related problem called the halting problem. The halting problem is, given a Turing machine, does it halt? Uh, which is a very basic thing related to all this. That is an example of a recognizable but not decidable language. A more basic example, or a related but also maybe a bit more fundamental example, is the ATM language, which is the set of all Turing machines, string pairs, where M is the description of a Turing machine, the description of a Turing machine, as a string. Okay? This writing Turing machines as strings is a delicate and important thing. You should look it up in the textbook, how you can do that. There are many natural ways of doing this, and W is in some sigma star, such that M on input W halts and accepts. the set of all Turing machines followed by strings W such that M halts on input W. And this is recognizable. This is somewhat easy to see, and the reason is the Turing machine just the Turing machine that shows that ATM is recognizable. It just simulates M on W, simulates M on W, the execution of N. ATM is not decidable. That's a serious theorem, and you will see that in a coming lecture. This is serious and brilliant. Okay, great. So that's all I wanted to say about decidable languages. I will wrap up by talking about enumerability and what and this is the origin of the word of the phrase recursively enumerable, but it's also a nice and basic notion. So a language is enumerable if, so just like Turing machines that accept and reject, you can talk about Turing machines that, okay, so far we have talked only about Turing machines that accept and reject. There are also Turing machines that can do other things. They can output values. How do they output values? Well, maybe they can have another tape and they can write symbols onto that tape. To that tape can be the output tape. To have to talk about such things in the formal definition of Turing machine, you'd have to update some things. Your transition function delta will no longer tell you what to write on the main tape, but it will also tell you what to write on the output tape. So things have to get updated in your notions. Uh, but we can talk about Turing machines that output things. So a language is enumerable. Language L is enumerable. If there is a Turing machine, Turing machine M with output tape, such that M on blank input tape, so it doesn't take any input. All it does is it outputs elements of L one by one on the output tape. M on blank input, just, no, I won't say just. M on blank input tape writes W1 blank, W2 blank, W3 blank on the output tape. Never halting. So it keeps writing, never halting, and such that this is an enumeration of all the elements of L, such that, okay, one, each Wi is an element of L. So these Wi's were strings, which actually take multiple locations on the tape. W2 is a big long string that takes multiple locations. Each Wi is in L. It only outputs strings which are in L. And two, for each X in L, some Wi equals X. It enumerates only strings from L and every string from L. So elements of L, all elements of L, and nothing but the elements of L, just like with truth. Good. That's when we say a language is enumerable. And a basic theorem, which is something you should try to prove, is that Turing recognizable languages are precisely the enumerable languages. So L is Turing recognizable if and only if L is enumerable. You can list out all the elements. I'll say in high level, in a few high level sentences, how one shows this. If the language is Turing recognizable, let's see how to enumerate the elements from it. Well, one way is, okay, go through all the strings in sigma star one by one, go to the first string. So if L was, so I'm starting with a recognizable language. So it has a Turing machine M that recognizes the language. So now go to all the strings of sigma star one by one and run M on each of them. As you run M on each of these strings, if you ever see M except, then you can print the string. But then you can output the string on the output table. That's part of your enumeration. But what if M on some input string is not going to halt? You can't commit to running M on that string all the way through to completion, because there may be no completion. So instead, you have to give, you shouldn't spend too much time running M on a string. You should keep coming back to the string and trying to run it for longer and longer amounts of time, but never actually run M all the way through to completion on any given input string. So the idea to enumerate the elements of L is to, for each I going from 1 to 3 all the way up to infinity, run M on each of the first I input strings for I steps. Along the way, if M halts and accepts on any of these strings, output all those strings. Sorry, output any string on which M halts and accepts. In this way, you can just keep running. In this way, you can, as I keeps going up to infinity, you can keep printing out various strings which are in L, and every string will end up being printed, because you know that there is some number of steps after which M on any input of L halts and accepts. The other direction is much easier. If L is enumerable and you want to know if a given string X is in the language, what you do is just start running the enumerator, see what all strings get printed. If you ever see X, halt and accept. If you don't, okay, too bad, you just die waiting. And so the Turing machine just continues and doesn't halt. Great. So that's this theorem. This is the source of the word enumerable in recursively enumerable, and it's itself quite a neat and interesting notion. There is a characterization of decidability in terms of enumerability. It's about enumerability in increasing lexicographic order. That's an interesting notion. You can try to formalize it and define it. Okay, great. That's all from me. Thanks.